So I'm Marcin Kostur, he's Artur Częsiok, and we will talk two of us. So basically I will use Artur to run the demo and change slides, right? Can you change the slide, please? Thanks. So Open Dream Kit is a project from European community, from so-called Horizon 2020. It's concerning virtual research environments. And this virtual research environments goes into a way how people do science, how people collaborate with each other, and how they present the data and how they publish the data, actually. And this is, there's a word, advancements of mathematics. So this project actually is run by mathematicians mostly. I'm a physicist, so I am like outside a little bit, but still taking part in this project. This is a huge project, 7 million euros, 15 universities, and about 50 participants. Yeah, and this is, we are going to the end like next year, so the project is pretty mature. Can you change it? And goals, what's the Open Dream Kit about? First of all, you can go to opendreamkit.org. Website, and there we have nice movies. What is actually the project? But in short, is a project about building these virtual research environments for mathematicians and other scientists and data scientists, of course, based on open source software, open source math software, and open collaborative tools and models. And we agreed, actually inside the project, so inside the timeline, we agreed that we are probably not going to really make like one kit. You can have an Open Dream Kit .install and you have one kit, but rather to build something which is flexible and everybody can fit it to its own needs. And this is very broad community. That's why it requires quite a lot of tools. And yeah, so those open source building blocks, they are including all the mathematics software, which are my colleagues from Paris mostly developing inside the project. But there's one thing actually, there's the first piece of software which was meant a little bit as a starting point was the SageMath. I don't know if anybody heard about SageMath. It's a huge project, including like 100 packages for mathematics, including even some of those GAP and algebra packages. And this project was having this notebook interface and was quite advanced in the time, like 10 years ago maybe. And now it's mathematical. So this is algebra, this computer algebra software, so it's for mathematical manipulations and also data visualization. It's based on Python very much. And the Jupyter, what's Jupyter here? Because it's not mathematical software. So Jupyter is an interface. It was actually produced based on the experiences of notebook systems like Mathematica and Maple had, and also this web notebook which was brought by Sage at some point. So the Jupyter project is now sponsored also by projects like this, which is, I think, very cool that European Commission is recognizing our efforts to create a better open source software and everybody can benefit, because I think most of you have used Jupyter. Yeah, what is the Jupyter notebook? What's the building block? So is there one person not having used once Jupyter notebook? So everybody knows what's Jupyter notebook, right? So it's of course open source web application is agnostic to languages. It can run many kernels, and it's having something like a rich output. And the rich output is very important because you can do something like write a paper. You can do those things just being in a notebook. And also you can have at the same time code, which is researchers, they like it very much. Data scientists, I see, like it very much. And it's very useful for education and any kind of interaction. And can I have a next? Yeah. These widgets. So the one element which is present in the Jupyter ecosystem and the Jupyter toolbox is widgets, which is interactive rich output, I would say in 3 words. It means that I can have something like an object on the Python side, which is having a counterpart in the JavaScript in the web browser world. And those two objects are connecting using some standardized protocols. and I can update a JavaScript object and get the update in the Python world, and vice versa. And it's a very simple idea. It's pretty much mature already. And this example, which is on the slide, is just showing a slider which you can move, and you can have the state of the slider almost immediately transferred to the kernel, to the server side. If somebody is using Jupyter as a local application and using just a web browser as a kind of advanced display, so maybe it's not so important that it's kind of client-server architecture. But on the other hand, it might happen that the data are somewhere in data center on a big fatty machines with number of GPUs. And we want to have still something which is interacting with them on our web browser, actually on our computer, right? So this then, in this case, this architecture is especially interesting. So this widget model is following. So we have this kernel Python, we have a widget object in the Python, and we have something in JavaScript which is communicating. And this is a building block which existed like a few years ago already. And K3D Jupyter, our project, our visualization widget is simply saying this widget for displaying 3D data in the web browser. Since web browsers, they are very capable recently. They actually give very direct access to most of the hardware which is used for data displaying. So we can use this possibility and make the software which is showing the data. And there's a bunch of software. So I am pretty sure that everybody saw the number of packages which we can show in the web browser, very advanced algorithms for visualization and very smooth visualization based on hardware. But in this case, we want to make it to use for the communication. We want to use this IP widgets system. So basically, the idea behind this software is that the plots are widgets in Jupyter system. This is mostly NumPy native, so we think about the structured arrays as a basic data structure, which is not always like this, but is our main point. We want to have like matplotlib feel and look, probably, so which is very nice because probably most of you tried matplotlib or similar software. We want to use Three.js maybe on the front end, because why should we just write in Scratch in WebGL? We can just use something which is a little bit higher. And for some data manipulations, we might want to have regular grids on the GPU sent and processed. So the regular grid first for the data processing. So this is our, so it's not like a, how would say, is our limitation, but we want to limit ourselves not to create something like Verge in our visualization toolkit as VTK is. Okay, so now we will show the demo, and it will be everything. Yeah. Actually, we were already the demo. So this, so we were already in the demo, but we don't want to show those plots. So this was actually done using the texture. For some reasons, we thought it's possible to put the texture on the 3D scene for visualization. A texture is like you can have a texture with 8 bits per pixel, and you can take the texture and calculate the texture on GPU, for example, from some high performance cluster, and just display the texture. So then you have the delays very small. So I say, okay, let's implement the textures, and this also is useful for presentations. Okay, so let's plot the point first. So we can plot the point. This is a point. I mean, it's just simply speaking the point. This is represented by some pixel shader, which is making those nice shiny features. We can change the pixel shader. Yeah, so this is 1 point, the data. We can make 2 points, of course. It's also possible. So we can change this pixel shader to, for example, yeah, to have some reflections. And we can change this pixel shadow to mesh, and we can draw those spheres in the proper mesh. Now they are not so nicely because you can see triangles, but they are now precise. So if you intersect them, can you intersect them or not? Can you increase the radius? Okay. Anyway, so we can draw a point. why sometimes it's important to draw one precisely to have a point which is represented by a sphere, and if you have two spheres close to each other, they are touching, not overlapping, not having some trick. Sometimes it's important to draw like 1 million of spheres. So can we draw more of them? Is it possible? We can take a random number generator, maybe reduce the diameter. Oh yeah, cool. And we can color them, why not? Yeah. There's not so many of them, but this widget is displaying easily like 10 millions of spheres if each sphere is represented as a pixel shader, one single simple pixel shader, not as a meshed surface with triangles. Okay, so there's not this rotation. If you notice, there's a loop. So the trick is everything in this widget and everything in a Python is connecting using IP widgets. So I am programming in Python, and I am having my output in the widget. It means that I can manipulate with those objects on the Python side, and it will be transferred automatically asynchronously to this widget. And it's working very nicely. For example, the camera, the plot object is having the whole scene, and the camera is itself is a few numbers, two angles and vectors of the camera. And I can manipulate them both ways. I can change my scene, read the camera, or I can set the camera programmatically like in this loop right now. And the data, of course, what we did was the same. We said that we took a plot, we replaced these 2 points by 10,000 points. Yeah? And it appeared after some while on the screen. It was pretty quick in this case. Okay, so if you have a plot, then we can remove this plot points and make a line. Yeah? Okay, we have also lines, so we have points and lines. And lines are having vertices. And now there's many ways to generate nice lines. So we take a random walk or Brownian motion. So it's very easy to generate in NumPy. You just generate Gaussian distributed points and in each direction, and you just commutatively sum it. And you get like trajectory of Brownian motion. You can draw many of them. I see it's quite fast. In this case, we didn't risk to run this on our server in Katowice because conferences and Wi-Fi sometimes it's not working. But if it's those experiments, if you run them remotely, they are pretty fast. I mean, this is like you got a little bit of delay because of the network and delays, but it's still pretty fast. So now we have how many lines we have? We have like 10 lines, 11 lines. And we can also draw the line with a tube. So there we have different renderers. So if you don't want just a very narrow line, you can make a line which is nicer sometimes. Okay, let's remove those lines. What else we have? We have surfaces. But this is like the simplest plot you can have. This is similar to the idea of Matplotlib 3D Toolkit. And so we have a surface, and you can notice that this constructor of the plot, this K3D surface, is taking height. And the height is a variable which is generated by some native NumPy method using mesh grid and so on. But this is just values of the function which has been sampled over some rectangular domain. Right, so this is two-dimensional array of values of the function, and if I give it to this plot, it will draw me these triangles and draw me this nice surface. What I can do, this surface plot is having a handle right now is plot PLT surface, and I can replace the values as many times as I want. And this is not just few data points; this is quite a lot of data points. I have 80 by 40 data points. Which is, I use float 32 arithmetics. This is my old GPU habits, just to use reduced arithmetics if it's possible, because, well, save the data. And we can just, so look at this, we can just run the sampling, this NP sine function on sum of squares plus some phase. When we change a phase, it's looking like a flowing wave. So I do a sampling actually in NumPy. In each step of this loop, right? And once I got it resampled, I send it automatically. It's being sent automatically to our widget. Okay, so we can add many other objects. We can sample the same data along some lines and draw those lines. We can calculate some vectors, draw vector fields. We got also primitives for this. Can we? Yes, we can. And so basically, this most common objects for mathematical plotting is present and is quite performant. This is our goal, and it's working nicely, I think. So now there's another thing we can draw boxes. So we can, once we have, you can imagine, then you can sample this domain, the three-dimensional domain. You can sample in three-dimensional space, and each box, each voxel under the curve will be marked as a box. Yeah, and we have facilities for this geometry. Of course, we don't want to do this with some sign of some squared, but it's very useful when displaying like with segmentation problems, like displaying some geometric data and some like CT scans, or for finite differences, some any numerical methods which are on regular grids. We have some kind of Minecraft style graphics to display this, and we use it quite often. Okay, let's remove it. Yeah. Why this surface? Why we actually? I mean, there's lots of demos on the internet when you have some moving surfaces. When you go to 3JS web page, it's very difficult to beat them. I mean, they have very excellent demos. But why is important? Important is because I can have my code, which is solving for me something in Python, some like partial differential equations, right? I can have this. In this case, this code, the cell above, is solving system two coupled partial differential equations in 2D, and I can solve them in Python. And if I want to visualize them, I can do it by sending it to our widget and plot them. Of course, I can do it also in Matplotlib, but even in Matplotlib, there is an interface, is a pixel, is just a one picture with pixels, right? And it's even rendering this picture is slower than using 3JS and WebGL possibilities. Okay, so the next interesting thing is also artificially invented problem. You have once again the same line, and what we do, we know the Lissajous curves. They are 2 dimensionals, but you can draw them just having this one phase. You can draw them in 3D by using the phase of the first oscillator. Lissajous is just a 2-dimensional harmonic oscillator, right? You can draw them. The trick is here not the Lissajous. This you can have a look in the Wikipedia or play around with this. But the trick is that we can change the frequency of those both oscillators, and we can change them using this slider here. It's IP widget, which is on our notebook. So we have one widget using communication through the kernel, sending back the calculated data, so the points of the line, to the other widget. Actually, what's possible, which you don't actually use often, but it's also possible to link to widgets on the JavaScript side. So you can link to widgets using Python code on the server side. You can link them on the JavaScript if you wanted. Okay, a little bit more aggressive is you can take a function of 3 variables, sample this function in 3 dimensions. So now it's 80 by 80 by 80 data set. And send this data set to our widget and say, do me matching cubes, so draw me isosurface on this data. So this is the case. So we have matching cubes method. And so what we do when we of course, this is isosurface for which value. So there is one parameter left, the value of the function which we want to have the isosurface at. So we can, of course, this is also connected with IP widgets, so we can change on the server side this value of this isosurface. And this software, this widget, will recalculate this using matching cubes, this isosurface. So this is now the whole data set is being sent to JavaScript. So there's quite a lot of data. If I want to update this like animation, like 20 frames per second, it might be difficult. But now the whole work of doing this isosurface is done by web browser. It doesn't need to be like this. Actually, it's completely not clear which data are we going to put to the web browser, which data are we going to preprocess on the server side. We can also run a matching cubes algorithm on the server and send the mesh to the browser. Then the sending will be quicker, but maybe it will be not done by GPU on the server. If you do it like in Python, maybe it will be not optimal. Okay, now this is our basic demo of possibilities to get a feel, and now we have some real our examples which we used. Most of cases we used in our work. Now is the idea where I process my data. We don't have unstructured meshes, unstructured volumetric meshes in K3D. I probably will not have them soon. The idea is there's so much software which does this on the server side. So why we should send the unstructured mesh, which is very difficult to deal with. So what we do, we take this, so in this case we have a geometry. This blue, more or less the blue area is the boundary of the geometry. We put a fluid inside and we solve it using some finite element solver to solve for the fluid flow. And this colors is velocity. So 0 is blue, that's why it's boundary. And we use some solver which is working on unstructured meshes. So there are tetrahedras somewhere in some random way oriented, and this is the data. So the data is unstructured mesh. So instead of sending this data to the web, to this K3D, we use a VTK, which was this 5 screens of code, which is very unpleasant to program VTK from Python and even not from Python. But we did this programming and we extracted the surface of this data, and we use the cutter in VTK, this bunch of filters. We can cut the surface in arbitrary places along this triangle, for example, without an interpolation, and and we can just send the surface to our widget. And you see when Arthur was changing this slider, actually there was a trigger, the computation on server side, which was taking the whole data set, the volumetric data set, doing this cuttings using this plane with some normal and some orientation position, and then sending this data and the fields with the square of velocity or magnetic velocity mapped as a color, sending this field as a mesh to our widget. We have actually VTK polydata, which is the only helper function actually, which is taking the VTK polydata, which is the surface mesh, so two-dimensional meshes, but in 3D, and this can be. It can be sent, but you see, this quite fast. I don't need to worry if I send like, I don't know, maybe it's like 20,000 vertices. If I send like 40,000 points to the system using internet, I can really have the server in Los Alamos. It's not a problem. You have like megabytes, maybe it's not that fast, but in this case, it's very, very good idea to pre-calculate something on the server side and send it. Yeah, there's this bunch of options, which is we have a flat shading, and we can show the meshes. We can make them like a little bit smooth. We can make them like really triangles to be triangles, and so on. Okay, let's move to another one. Streamlines. So once we have the calculations, this is more or less the same. Now this is interesting. This is volume rendered fluid flow. Volume rendering is implemented in K3D. On regular grids. In this case, we didn't have the same data from the simulation from finite elements. We have this data from simulation or lattice-Boltzmann, which is on regular grids. And you can volume render something which is inside. So say you can have to send everything to the browser and do the volume rendering on the browser side. And it's useful. And now, of course, once you have a fluid, you can have something like streamlines. So you can follow the fluid path when the flows goes, yeah, and this is just streamlines, and this is also a very useful thing for visualization of fluid dynamics. Can we go to the next one? We have 5 minutes. And so this is like how many points we can draw, because just drawing 2 points and maybe 20,000 is not that exciting. So Arthur was digging for a good example for today's, and he found this Kaggle data set for New York City taxi for predictions, and there are like 5 million, actually 10 millions. There are two sets, 10 millions of points, and we can draw those points using our widget just in a browser, and it works. Yes, 10 million points is not that little. Of course, you don't want to render each point with triangles. We have to do 1.1 pixel shadow and not know anything else. But of course, we have a texture, so we can calibrate the map and make the points to be on the map. The points are in 3D, so the third dimension can be price of a taxi drive. And of course, because of the interactivity, we can filter those points and send just a portion of this and update the data set with a slider, and we can build applications like this in minutes. Well, Arthur can do it in minutes, maybe we need hours, but nevertheless, in almost interactive time. Okay, let's leave the taxi. Segmentation is 3D data. So we have matching cubes for 3D data representation. We have volume rendering, which we'll show later, and we also have voxel geometry. So this is a CT scan of some patient with his chest, and there is a heart, and we want to select one tiny piece called coronary artery, and we want to have this piece and one fluid simulations maybe on this. So this is actually a boundary. Yeah. Now we have the so-called ground truth. So the yellow surface, actually this is represented as surface, I think it is. So this yellow surface is we know that our artery is looking like this. We know our scan is this red one, and we want to test some algorithm of segmentation and compare it voxel by voxel. So what we do, we can run our algorithm, which was in the cell above. We can run an algorithm and then use this voxel method to draw those voxels, so to draw the Minecraft-like geometry, voxels on the top of everything, and then you can of course draw the true positive, false positive. We can subtract, remove one, add one, and we do it all from Python. These data sets are not that small. There is no sparsity assumed, so we send all the time the full data sets, except we do compress. So if there are zeros, it's compressed very well. Nevertheless, it's pretty useful. So we have 2 minutes left. So if you can, we move to CT, I think. So one very interesting visualization technique, which is definitely the future, is a volume rendering. And so when you have a tomogram of computed tomograph of a patient, so you can have a volumetric data. How to see this data? You can try to select some boundaries between artery and something. And this is a complicated process, but you can take the data and do the volume rendering just as it is. And this is volume renderer with few features which are advanced. So we have these surfaces are shiny. We calculate gradients. There is a shadow, and the shadow is updated with some controls. And in this data, you can see that this is going the direction of cinematic volume rendering, which you can say, okay, this is a surface, it's not a volume, but it's really the volume data. There's no surface has been calculated. This volume rendering techniques, the data set you can have a look is about 500 times 500 times 300 pixels, voxels actually. Yeah, so it's quite a lot of data. It's about 100 megabytes. And the data sets are sometimes even bigger. The problem is JavaScript, because JavaScript doesn't like to have more than 1 gigabyte of memory used. I don't know why, but hope it will change. And this technique, if you want to run everything possible on this data, if you want to run very high resolution shadows and very high resolution integration of the data, then it will require many GPUs to render. This is gaming quality. Gaming quality laptop, so it's having maybe 1/3 of the power of the fastest GPU, and it can do pretty nicely. Of course, we tune it down so it's interactive. You can very easily make it non-interactive if you're not careful. So that just to make sure the volume rendering means that I take the whole big volume, and each pixel on the screen is integrating the volume through it. And there are also many tricks and many such integrations done for shadows and everything else. So, and we have 21 seconds left, so I think it's the time to show the last slide. Well, yeah, where is the last slide? So if you want to, that was okay. I mean, he doesn't like Google. Okay, PowerPoint, yeah. I knew it. Yeah. Yeah, I have to learn. Okay. Go to last slide. Okay, so thank you. And of course, GitHub and installation instructions are here. Any questions? Yes.
Are these notebooks available as examples online?
Yes and no, not exactly the same, but similar they are, and we will probably update examples. We are very bad at updating examples and documentation. And we're working right now, but most of them, yes, it is. Yeah, we have very similar examples at this. Some of those examples they are not nice because you have to download like gigabyte of data, but still you can. We don't need to host them. So yes, yeah. Yes. We didn't, well, there are a few tricks you can do. I mean, this is, of course, we don't want to make full application in JavaScript because this is growing. So we say, well, let's have the basic controls. And the basic control is not that basic, but you can take a screenshot, manipulate with some parameters, with some objects. So you can turn off visibility. So you have some basic control on the widget. Of course, when you click on something, it's synchronized with the Python. So you have two ways of controlling the object from this menu and from this Python kernel side. Yeah. Yes and no. Yes. Yeah, you can say something. Okay, well, the transparency is a tricky story because it depends on the order. We wanted to keep it like fast, quick, and not like clumsy. So we eventually put some transparency. In the last examples, I think in this, no, we didn't show the example. When you have a point cloud, you want to see the density, and so it's nice to have transparency. But we didn't care about the order too much. So in this sense, we probably will implement it, and it's not. I think it's in devel now. Yeah? Or isn't it? Yeah.
Sorry for interrupting, but we are a bit behind schedule. So thank you very much.
Thank you.